Hi everyone. So from now on, I'll make sure to cover up all your syllabus of chemistry of BSc obviously. And for today, we have the chapter S block elements. Well, the book that I am using here is Inorganic Chemistry by Modern, and it is for gndu. Okay, so if you are in other universities, then still you can watch this video. You can just go and check out the syllabus, and whatever topic is left, you can just comment it down. I'll make a video, separate video for that as well. No problem with that. So I'll try to cover the entire chapter in just one single video. So if your exam is tomorrow, here is your video. Okay, so let's get started with S block elements. See, now we are in BSc and we are not a child anymore. So we need not read each and every sentence because questions like these are not asked. So whatever would be asked in your exam, I have already highlighted that because I have already taught students with this book. So you can see I have messed it up. But obviously whatever is important, I have highlighted it and I'll telling you about the same in this video as well. Okay, you need not learn everything because everything is not going to come in exam. Whatever is going to come in exam, you'll be seeing that in the video. Okay, so let's get started with S block elements. We all have seen the periodic table, haven't we? Have a look at it. So we are going to discuss these two lines today. What are these two lines? These are the two groups. Okay, so this is the first and the second group according to the modern periodic table that we are going to study. Starting from here. So the S block comprises of two blocks. Like this is the first block, come on. This is the first and this is the second block. So this first block is the S block 1 and the second one is the S block 2. So the questions that would be asked, let me tell you the major questions right from here. The questions would be the similarities between one block, how these elements are similar to each other, or how the first element is different than rest of the elements. Two questions, same questions from here as well. How are they similar? How is the first one different? These two questions, similar answers. Second question that can be asked is about the anomalous behavior. Anomalous means a different behavior. How is the different behavior? See, lithium, magnesium, sodium, calcium, potassium, strontium, they have some sort of relationship. The properties shown by lithium and magnesium are quite similar. And what are those properties and why are they similar? We are going to study about them. These are the major questions that are asked in each and every exam that you give out there. Okay, so let's get started with this S block. So at first we need to see what are the elements, right? For starting with group 1 elements, we have here the list. See, hydrogen is not included in the list. Rest all the elements are there. Lithium, sodium, potassium, rubidium, cesium and francium. How I remember them is by LINAC. Lithium, sodium, potassium. Then you have rubidium, cesium, francium. LINAC, rubidium, cesium, francium. That's it. That's all you have to remember about group 1. So, starting with group 1 only, abundance and occurrence. Hardly you'll see any question regarding this abundance and occurrence, and it's totally a theoretical question. You need not listen to videos on this topic because that's not even required. Okay, so if you want to do it or you have seen previous papers of your university asking questions about this, then how you're going to do it, let me tell you in just one single step. Calcium is the 5th most abundant element in the earth's crust. So what we got to know what calcium is, calcium, or you can just write Ca, the element's symbol. Now it's 5th most abundant. Done. First point is done. Then what we have in the list, and hence the 3rd most abundant metal. See, what is the difference between element and metal? Okay, all the elements, they are not metal. They can be non-metal, they can be metal, they can be metalloids, right? But there are the metals. See, the bigger group is element, the smaller group is metal. Okay, so this is 3rd most abundant metal. Done. What else do we have here in the list? Vast sedimentary deposits of calcium carbonate occur over the large parts of Earth's surface. So here we have CaCO3, abundantly, available. That's it. These are the points. And do you think these kind of questions would be asked in the examination? I don't think so. So let's skip this point. If you want to go through it, you can write these kind of points and that's it. You need not learn. See, whenever you have an exam next day, you cannot spend your nights reading the lines. You have to write these kind of things. And trust me, you can also, if you are good at doing all this, either you keep a separate notebook, because I know most of the students in BSc don't do that, but you should be doing it. Maybe because you have to go for your masters, maybe you have to go for entrance tests of foreign universities or whatever. Okay, so for that you should be keeping a notebook, or which is my favorite part is, you can always keep a page. Right, a page. You can staple a page here, and whatever important things of this page given in this book, you can write it over that page as well. But obviously I'm good at messing up with books. Okay, now let us have a look at the electronic configurations. Now the electronic configuration of group 1 and group 2 are given. You may be asked about the electronic configuration of group 1, and that would be for 1 mark, or for group 2 that would be of 1 mark as well. Now how do we write it? Let's start up by looking at the periodic table only. See, we all know that this line, this 18th group, it is of the noble gases, right? Do you remember that? So these noble gases, and see, after helium we have lithium in the list. Then we have neon, and after neon we directly, the adjacent one is sodium. Argon, potassium, xenon, rubidium. Is it so? Wait a minute. Oh, sorry, I messed it up a bit. Argon, potassium, krypton, rubidium, xenon, cesium, radon, and francium. So you can see they are followed, they are like this noble gas configuration plus 1 in the S block, because obviously they are in S now. So this has to be like this, NS1. Here it's going to be a noble gas configuration. Then you will have the number like 2S1, 3S1, 4S1, 5S1, 6S1 and 7S1. Do you get that point? So see, it's written over here as well. Helium 2S1, neon 3S1, argon 4S1, krypton 5S1, xenon 6S1, radon 7S1. This is the electronic configuration of each one of them. Easy. Now the same thing is here for this one as well. So how are you going to write it? It's going to be like this only. The normal, so you are going to write the general configuration is this, NS1, after the noble gas configuration, right? And then you may list a few of the examples, like for lithium, sodium and potassium, because you know that they are preceded by which elements. Then the same is for them also. You are going to write it that, see, a noble gas configuration, this like for helium, and then what you have, 1 and 2, NS2, 2 elements in the S, 2 electrons in the S1. Okay, it's going to be like this, NS1, NS2. That's it. See, have a look at it. Helium 2s2, neon 3s2, argon 4s2, krypton 5s2, xenon 6s2 and radon 7s2. Here one element is there in the S block, 1 electron is there in the S block. Here the 2 electrons, the 2 outer electrons are there in the outermost S block. Easy, very easy, just you have to go through it. See, all the alkali metal have 1 electron in the outermost S orbital, while the alkaline earth metal have 2 electron in the outermost S orbital, preceded by the noble gas configuration. This is the basic line that you may remember as it is as well. See, alkali metals and alkaline earth metal, what are these? The first group, this one, I should keep it like this only, this one sorry, this is alkali earth metal and this one is alkaline earth metals. Done? Easy. Now comparative study of the general characteristic of group 1 elements. Now you are going to compare them. I told you now how are they similar to each other. Now that is what we are going to cover here. So you need not memorize it like this, like in the lines. No, you don't need to do that. You can always keep points. See, I have highlighted largest atomic ionic radii, and then this is important. So we are going to highlight things like that only, and you can have a look at them. They are around 10 physical properties are there, and you are going to find the similar physical property for second group as well. So I'm going to lay more emphasis on them, and then for the second one I'll just read it over. physical properties, atomic or ionic radii. I know this thing very well that we have done this in the earlier classes, like in +1, +2 as well. So you must be knowing all these points. I just have to recapitalize all of them. Okay, atomic and ionic radii. See, here we have lithium, correct? Let me draw lithium. Now, we all know that when we will move here like this in the period, right? From left to right in the period, when we'll be moving, see that number of shell is going to remain the same. See, 2s1, 2s2, and it's all 2 shells, right? So it's going to, number of the outermost shell, it's going to be the same, 2s2 and then 2p1, 2, 2, 2, 2, 2. That means the number of shell remains the same. But did you notice I reduced their size? Why is this so? See, as the number of shell is the same, so in outermost electron would be there in the 2s shell only, 2s or 2p shell only, right? Electrons would be there only. And now as the number of protons increases, the nuclear charge would increase. Number of protons increases, then the nuclear charge would increase. That is, the positive charge would increase, and then the nucleus will love to, it will love to hold the electron more toward itself. It will tightly hold the electron. It will start attracting electron toward itself, and then the shell will shrink. We can just use the word shrink, not in the answers, but just to understand the topic. See, nucleus is there in the center. There are electrons here in this ring, and the nuclear charge, as it keeps on increasing, it attracts electron more and more toward itself, thereby reducing the size of the atoms or the elements, right? So that's why moving from left to right in the period, the size decreases. So what we can say is they have the largest atomic and ionic radii in their respective periods. See, it is not just for lithium. The same would be there for sodium, potassium. You can even draw them. When we were kids, just forget this number, it's not of any use. Okay, when we were kids, alright, in +1, +2, I drew you something like this. 1, and then again, as the size increases downwards, so I drew something like this. And then I never forget about this. You can do the same as well. On moving down the group, what happens is that, see, when we move down the group, number of shell, 2, 3, 4, 5, 6, 7, number of shell keeps on adding. Like it was the second one, consider it was it was the first one, then the second one, then the third one, then the fourth one, then the fifth, then the sixth, then the seventh. See, the number of shell keeps on increasing, right? So as the number of shell is increasing at a much faster pace than the increase in nuclear charge, therefore the attraction would be less. So because of the lesser and lesser attraction, the electrons will drift apart, therefore making a larger and even larger shell as we move down the group. See, alkali metal have the largest atomic and ionic radii in the respective periods. On moving down the group, the atomic and ionic radii increases. This is due to the fact that the alkali metals are the first elements of each period. They are the first of each period, right? Now, as we move in a period, the atomic radii tend to decrease due to increase in effective nuclear charge. See, we all know that one electron keeps on adding, right? One electron keeps on adding to the shell. Like here for lithium, we just had 1. Okay, so let us draw a bigger lithium here only. We had 1 electron, then we had 2 electron, then we had 3 electron. I am not considering the P and S, whatever difference there is. Then we have 4 electrons. As the number of electrons is also increasing, but the number of protons is also increasing. And as the number of shell remain the same, nuclear charge overpowers, and therefore the size decreases. Done? Now, therefore the alkali metal have the largest size. Now, on moving down the group, there is increase in the number of shell. As the number of shells increases, okay, so as the number of shell increases, their radii is going to increase, because the effective nuclear charge it does not increase as much as this. So as we move down the group, size increases. Along the period, size decreases. Increases, decreases. Okay. First point was the most basic one. The rest all the points would be covered on the basis of this only. Next, ionization energies. Alkali metals have the lowest ionization energy. Now, what do you mean by ionization energy in the first place? Ionization energy means the energy that is required to expel, to remove out the electron from the shell. That is the energy that is required to remove this electron. So that, because we all know what is the configuration. The configuration is like this, right? So if I'll remove this one single, see, NS1 means it is like 2S1, 3S1, 4S1 starting from 2. N's value start from 2. You can mention it. N greater than equal to 2. Okay. And less than 7. Like this. Okay. So when we will remove this one, you will get the noble gas configuration. See, everybody wants to get that noble gas configuration. I don't want to have an extra electron with me. I want the noble gas configuration, the stable configuration. And in order to get the stable configuration, I would readily remove this one electron. I would want to remove this one electron, and very less energy would be required to remove this electron. Is it true? Obviously. See, and now comparing with this period elements, see the second one. Here you have to remove 2 electrons. Is it easy to remove 1 electron or 2 electrons? Obviously, it is easy to remove 1 electron. So ionization energy, the requirement of energy would be low. We would need less energy to remove it, right? So more and more energy would be required for removing 3, 4, 5, 6, 7 electrons. So their ionization energy is the lowest in the period. Right? Now, within the group, their ionization increases, ionization energy decreases down the group. Why is it so? Now compare this as well. This is the nucleus. This is lithium. This is the nucleus. This is considered cesium. Okay. As the size has increased, now the distance from the nucleus, the distance of the electron from the nucleus has increased. Now the nucleus is not pulling electrons strongly. It's like this case. Here the electron lives with his parents. So the parents have very much influence over him. So whenever their friends want, so they have to take permission from their parents, right? But in this case, they live in 2 different countries. There's very large difference between them. So do you think every time this electron has to ask his or parents to go for a party or to leave home? No. The influence would be less influence. So very less energy. Just a phone call is required. Oh, I am standing out of your house. Let's go out. This much is required to remove the electron from its place. Okay. So the ionization energy increases along the period but decreases down the group. Okay. So this is something that you can remember. Now, how do you represent an ionization has taken place? This is how you represent ionization taking place. This is a metal. Now it turned into an ion and an electron is expelled out. Now you can take example of sodium. It became sodium positive and an electron is left out. Now considering the second, see there is a large difference, around 10 times, right? Around 10 times, 9 to 10 times there is a difference between the two. Why is it so? See, when we removed the first electron, it got the noble gas configuration. See, when sodium will leave one electron, it will turn into a neon and it has a stable configuration, right? And now it is very difficult to remove one electron from a stable gas configuration. If you will remove one electron, it would be very, very difficult to remove it because the configuration is stable. Now you do not want to move, you do not want to lose or gain electron. So the first ionization energy, you can write it. See, this is written. Along with that, you can just write first ionization energy is low, low, low. Second ionization energy is high, high, high. This shows this is very low and this is very high. Let me have a look. Is there any empty page in here? I can wait a minute. Let me check if there is any empty space. There I can tell you how to write points. Okay. So the first point was about atomic and ionic radii. So I am just writing radii. Okay, so the radii increases down the group. So I'm writing the symbol like this. And it decreases along the period. First point is done. Now second point, ionization energy, it increases along the period and decreases down the group. Moreover, first ionization energy is very much less than the second ionization energy. Now you do not need everything. For this you can answer effective nuclear charge for the increase. Okay, and here for the ionization energy, again the point is the noble gas configuration. You just need to write points like this, and that's it. See, you have covered up 2 entire paragraphs in this much only. Now you have melting and boiling points, and the melting and boiling point that all you need to remember is low melting and boiling points. Just because one electron is there, so you can easily move that electron, and that's it. So these kind of points will not be discussed in detail. You just need to know low melting point, right? And the melting point decrease on moving down the group and decreases as well. Low melting point and it decreases down the group. Second point is done. Now we need to know about the density. Density's formula is mass divided by the volume. So the mass divided by the volume. Now we are going to see whether the mass increases more or the volume increases more. If the mass increases more, density increases. But if the volume increases more, density decreases. Now we are just going to compare them for along the period and down the group. The density of alkali metals are quite low as compared to the other metals. So for all the metals we have said that density are low. Okay. Now lithium, sodium, potassium are lighter than water. The density increase on moving down the group. So the third point that you are going to write over here would be like density increases on moving down the group. Density increases down the group. Okay. Now the alkali metal have close packing of metal atom in their lattice, and because of the large size of the atom they have low densities. This is because as we move down the group, see what will happen. Sorry. As we will move down the group, see the density is increasing or moving down the group because the mass keeps on adding more and more. So the density increases as we move down the group. Now the density of the metal depend upon the packaging that they have. The alkali metal have close packing in their lattice, and because the large size of their atom they have low densities because the atom are of large size and their packaging is quite of that stuff. Packaging is tight. Okay. Now as we move down the group from lithium to cesium, there is an increase in the atomic size and mass. See, as we move down the group, mass increases, right? The mass is going to add up every time. From moving from here to here, then to here to here, the mass increases. 22, 39, 85, 132, 320, 223, right? The mass is increasing. Okay, mass is increasing and the volume is also increasing because the size is also increasing. Now what will we consider? Which one is increasing at a faster pace? That will give you the answer. As we move down the group, these two changes are there, but the increase in mass is more than increase in size. So I told you, increase in mass is more. I told in the right beginning, then I told you there is an increase in the density. That means there is an increase in mass more than the increase in volume. So here you can write is for first block. Okay. So here you can write the reason for this is mass increases more than the volume. So change in mass is change more than change in volume. That's it. Okay. So now as a result the density is increasing, that we know. However, potassium is lighter than sodium, probably due to the larger atomic size as compared to the atomic mass. It may be noted that they have lower densities as compared to the rest, all of them. So it increases down the group, decreases along the period. That's you can write. Now electropositive character. Electropositive character means their character or their ability to lose an electron. Okay, and that is the property of a metal. So this is also called a metallic property, and the electropositive character is very nice. Why? Because they have a tendency to lose an electron, and they easily lose an electron. Now all the alkali matter are strongly electropositive. Okay, now let's go on. These elements are therefore said to have strong electropositive character. Since the ionization energy decreases down the group, they are more and more electropositive. See, electropositive is the ability to lose electron on their own without getting any energy. So when we move down the group, they want to move their electron. See, when we are moving down the group, the electron is completely ready to to exit the element, and it will get the noble gas configuration. So the electropositive character increases down the group. Okay. Now oxidation states. So they have the +1 oxidation state because they have the ability to lose one electron. So they have +1 oxidation state like this. So they are called monovalent. That is just a theoretical point. Now characteristic flame coloration. So they gave special colors to the flame. So these are the colors that they have added. See what will happen. We all know, because they will lose one electron. They have one valence electron. So that valence electron, when it will get heat, it will get excited, and then it will impart colors. As you know, it get impart. See, this is the lower energy state. It will go to the higher energy state, and as the higher energy state are unstable, it will come down, thereby liberating color. We have listened to this point from so many centuries now. Now photoelectric effect. Because they have an electron that can be ejected, so that's why they show photoelectric effect. Nature of the compound, they form ionic bonds. So these are the points that you have to write. Photoelectric effect, positive, that is they show. Nature of the compound, ionic bonds. Now lattice energies. The alkali metal salt consists of cations and anions, which are held up by strong electrostatic forces of attraction. What are the alkali salts? Alkali metal salts. That means the metal, one part would be the metal and other thing would be this any of the other element, like NaCl, that is sodium chloride. Here sodium is an alkali metal and chloride is the second counterpart, and we are talking about these things. See, Na is positive, Cl is negative, so they have strong electrostatic forces of attraction. Therefore the lattice energies are very high. One positive, one negative, high lattice energy, because there's a high attraction, force of attraction between them. And as we move down the group, the lattice energy is seen to be decreasing. Why is this so? See the sizes. Let us talk about the sizes. Their sizes are quite comparable. Lithium and chlorine. Then we have sodium and chlorine. Again, their sizes are quite comparable. But as we move from cesium and chlorine, see, are their sizes comparable? No. That's why the energy decreases, because it is really difficult to adjust them. Now talking about sodium and fluorine, their sizes are comparable. Sodium and chlorine, their sizes are a bit uncomparable. Then sodium and bromine, sodium and iodine, are the sizes comparable? No, they are not. Therefore the lattice energy decreases like this. Lattice energy calls for the stability. They are stable, they are a bit less stable, and they are least stable. Similarly for that one also. Now we are going to have a look at the group 2 elements along with this also. Same physical properties are shown by group 2 elements as well. Where are the group 2 elements? Come on. Or they haven't given it in this. Here it is. Okay, here it is. See the atomic and ionic radii. Again, it will decrease along the period, and their atomic radii would be less than the group 1 elements. So their one would be the less than the group 1 elements. Main comparison would be there only. Density you can read. Melting and boiling point, again low. Okay, but higher than the alkali ones. You can write it this. Ionization energy higher than 1. First ionization energy is higher than the first ionization energy of the group 1 elements, but the second ionization energy, which we write at IE2, that is less than the ionization energy required to remove the second electron from the group 1 elements. This is the point that you have to write. If you know the basics, then these things are pretty much easy. Now electropositive character, they are less electropositive, right? Less electropositive, or you can write like this, group 2, group 1, right? And the characteristic colors that they give to the flame, they are there. Now tendency to form bivalent ions. So they were monovalent, their oxidation state was 1, their oxidation state is 2, because they want to remove 2 electrons rather than removing just 1 electron. Divalent, and after getting divalent, they have stable noble gas configuration. Moreover, in solution, the +2 of the alkaline are extensively hydrated. High hydration energy makes them more stable. So first point was noble gas configuration. Second is the hydration energy. They say that the +2, they get more hydrated. So that's why. Then the third one, in the solid state, divalent forms stronger lattice. So stronger lattice in the solid state. In the solution state, they are highly hydrated too, and they also get the noble gas configuration. This question you can expect for 3 marks. Okay, so these are the 3 reasons that have been provided along with it. Now, before going into this detail, we have chemical properties as well. See, the chemical properties are something that even if I tell you about it, you will have to memorize them as well. Okay, so see, their chemical reactivity is very high because they have low ionization energy. They can easily remove 1 electron, and their electron can get anywhere and can make any reactions, and they have low heat of atomization. Now, action with air. How do they react with air? They can combine with oxygen in 3 forms: normal oxide, O2 negative, peroxide, O2 negative, and superoxide, O2 negative, whatever it is there. This is the action with air, and they have explained this. Now, what are the oxides that are formed? So you have examples for each case, for peroxide and for superoxides. This is something that you need to memorize. Okay, then you have action with hydrogen, then they form hydrides. Then again you have points. The reactivity of alkali metal with hydrogen increases from lithium to cesium. They are more and more reactive toward hydrogen when we move down the group, right? So these kind of points are provided with it. If you will want it, I'll cover it in separate video. Otherwise, this video will be more than 2 hours, lengthier than 2-hour video. Okay, so the chemical properties would be covered up in detail if you want, and if you comment out for it, only then it will be in a separate video. Otherwise, in this video, I'll just suggest that these are the things that you need to memorize. Okay, so you can do that. We are going to look at the questions that are directly asked. Okay, my main concern is about them only. Now let us have a look about the anomalous behavior of lithium. Anomalous behavior of lithium and the diagonal relationship. Okay, in the beginning, I think I instead of using the diagonal relationship term, I used the term anomalous. So that was wrong. Okay, pardon for that. Now, anomalous behavior of lithium means how is lithium different than other members of the group? How is lithium different? Similarly, anomalous behavior of beryllium means how is beryllium different than other members of the group? Why are they different? So first we look for lithium, and then we look for beryllium, and after that we'll look for the diagonal relationships. Okay, why? So the first question is, why are they different? So these are the reasons why are they different. Size of the lithium very small, because we know that the size increases down the group like this, and now we are comparing just these. Okay, as the size is minimum, so minimum size, high ionization energy, and least electropositive character. More, because the electron is here and the electron is here. See, we all know that more energy would be required in this case to remove the electron. So the first point was small size. Second point, ionization energy high. Polarizing power is quite high due to its small size, which result in covalent character. Polarizing power high, covalent character, rest are ionic in nature. It do not have any vacant d orbital. See, it is all it is just having S and not D. Just have a look at this. See, all the other elements that we are going to consider, like considering these cases, they all have some D's inside them, right? They all have some empty D orbital, but lithium do not have any kind of D orbital in it. So, no vacant D orbital. Fourth point is no vacant D orbital. Done. Now, these are the reasons, these are the whys, why lithium is different, and these why are the same for beryllium. Let's do that also. See, the why. Small size, 1. High ionization, 2. Absence of D, 3. High polarization, 4. These are the 4 same reasons for, beryllium and lithium. Same to same. That's why I have written for lithium. The same would be there for beryllium. Where were we? Okay. So how is it different? Right? Now these were why. Why is it different? Now these are how is it different? How do we know that the lithium is different than others? It is hardest. Melting boiling point is higher. Less reactive. Form only monoxides. Rest form peroxide and superoxide as well. Okay, hardest, number 1. Melting boiling point high, number 2. Less reactive, number 3. Monoxide only, number 4. They have lower ionic characteristics. Their salts have lower ionic characteristic, number 5. At least 5 points you have to memorize. Then you can go for this. Lithium chloride and nitrate are soluble in alcohol. Rest are insoluble. Lithium hydroxide is less basic. Okay, so these are the points that you can memorize. Okay, and lithium ions and its compound are heavily hydrated. So these are the points. See, the first 5 points that we have already done: less reactive, hardest, high boiling point, monoxide, and lower ionic characters. And then you have, its hydroxide is less basic, heavily hydrated. So 7 points, we have done 7, and you can do even more points if you want to. Otherwise 5 to 6 points are good enough. Now we are going to look for the same in beryllium as well. See, in beryllium, harder than rest of the members. So it is harder. Then melting boiling point is high. First 2 points are exactly the same. Yes, beryllium do not react with water, but others do. Beryllium do not combine directly to form hydride, other do. Beryllium form covalent bond, rest form ionic. We have done the same for lithium as well. Beryllium carbide with water gives methane, there gives acetylene. Or BeO is amphoteric, MgO is basic. So these are the points that you can do. Okay, so 5 points at least for both the cases. Lithium one was easy. Same points, 2 to 3 points directly are same for beryllium as well. Okay, so with this, your very important question about the anomalous behavior of both, that is of lithium and of beryllium, are done. Now we have to look for the diagonal relationship, that lithium and magnesium has some sort of relationship. Their properties are same. For beryllium we have aluminium. Lithium, magnesium, beryllium, aluminium. Now have a look at the definition of diagonal relationship. It has been observed that some elements of second period show similarity with the elements of the third period diagonally. See, the one in the second period, they have some similarities with those in the third period, and they are present diagonally. Okay, sorry for this disturbance. Right, thus the similarity in the properties of the element present diagonally is called diagonal relationship. Diagonal relationship is the relationship that shows the similarity in the elements that are present diagonally. Why is this so? Just a simple answer. See, we know the size increases down the group and decreases along the period. Here it increases, here it decreases. So diagonally it will neither increase nor decrease. It will be the same. Same goes for beryllium as well. Okay. So the number 1 point was for size. Again same. Now let's talk about the ionization energy. We know that the ionization energy, it is about the size. Okay. Then the ionization energy, we know it decreases down the group, but ionization energy increases along the period. Here it increases, here it decreases, here it will be the same. So similar points are there that we are going to consider. Number 1, why, that is cause. Then number 2, how. See, similar electropositive character, just like I told you about the ionization energy, right? The same is for the electropositive character. As the ionization energy decreases down the group, so the electropositive character, ability to lose electron, increases. So it increases, here it decreases, so diagonally it relates the same, similar. So first point was, instead of ionization energy, we have electropositivity. You can along with this add the point about size, point about electropositive character, then is about the polarizing power. Now, on moving from left to right in the period, ionic charge increases while the ionic size decreasing, thus causing an increase in the polarizing power. See, this is like a magnetic behavior. Okay, so as the size of the magnet is decreasing, but the magnetic abilities are increasing. See, the charge is increasing. The charge keeps on increasing as the size is decreasing. So the small magnet, it will become a very powerful magnet because it has more and more, because it is concentrated in a more and more smaller space, like that. See, bigger one with a small positive charge, smaller one with a bigger positive charge. That's why it is more polarizing. So when we move left to right, polarizing power increases, but down the group it decreases. So diagonally it relates the same. Number 1, size, electropositive, polarizing power. See, you can compare it like this. Here it is, polarizing power increases, but down the group it decreases. You can always remember it like this diagram. You draw this diagram and in your exams you will get to know, yes, this is the point that you have to write. Here it increases, here it decreases. At first you have to draw the size and then you have to put the plus symbol. As you move like this, the plus symbol should increase, and as you move like this, plus symbol may remain the same as well. So here it increases, here it decreases, so here it remains the same. These are the 2 points here. See, the similar points are here. I am telling you about like this, they have not written, you have to write the same points like that. You have to write about the size, about electropositive character, and the third one about the polarizing power. Done? Okay, now a look at the similarities, which is, I think it's not of that much importance because it's something theoretical only, like this. I need to first see for them. Where is it? Here it is. Now see, atomic radius similar. So if you are writing atomic radius similar, ionic radius similar, quite hard, electronegativity is similar, polarizing power same. See, points that we have written above, they are the same. At first we wrote about the size, now 2 points are there for the radius. Then hardness. Then we have written about electropositivity, here we are writing about electronegativity. Then polarizing power, this point is again the repeated one. So 4 points are directly similar. Okay, and then you have the both form their hydroxide are weak bases, 5 points. Okay, and after that they are hard in nature, 6 points. Done. After that you can keep any point which you like, any point. Their hydroxide is weak base. See, this point is repeated. Okay, so if you have many points, then you may repeat a point to make the number even more. See, we are going to write about ionic radius, atomic radius, electronegativity, polarizing power, weak bases, hard nature. 6 points, very easy, very easy, which you can do in just 1 minute, right? You can repeat like this, and just give it like this: atomic radius, ionic radius, then electronegativity, polarizing power, then weak bases, then hard. 6 points are done. Then you may take up any 1 or 2 points from the rest. Okay, now look at the same thing for beryllium and aluminium as well. They both form covalent character. You can write the same one as well. At first, atomic, ionic radii are same. Okay, then after that you can write the point for same electronegativity, same polarizing power, and then your fifth point is for the covalent bond. So they both form covalent bonds. Both metal are weakly electropositive. See, I told you about the point of electropositivity, and very important point over here is BeCl2 like Al2Cl6 have a bridged polymeric structure. You have to write this. Very important point, because this is something that we are going to do as well. This is from the chemical properties which we will be doing in this video also. Beryllium chloride like aluminium chloride has a bridged polymeric structure. Okay, they have polymeric structure. Done. I think there should be a point for amphoteric nature. Yes, there is an amphoteric nature point as well. Okay, so they both form amphoteric oxides. See, very much we have done around 5 points, right? We did with this one. 5 points were done till there. Then you have 2 more points to add. Then 7 points. They are good enough. Okay, after that we have properties for special features of the hydride, from which we have to do solvation and complexation tendencies, and then you have the role of alkali and alkaline earth metals in the biological system. Charging of my phone is just 18%, and I think I will not be able to cover up in this video. We have to make a second part. That's a sad part here, but anyhow I'll link it in the description as well when I'll upload it there. Okay, so we will do BeCl2 in that. Stay tuned for that. Okay, BeCl2, we will do the solvation and complexation tendencies, second topic, and we will do this role of alkali and alkaline earth metal in that as well. So these 3 questions would be covered in them, and with that most of the questions that would be asked from S block elements would be answered. Okay, so 3 topics are left, and rest we have done everything except the chemical properties, and out of the chemical properties the questions that would be asked I will cover them as well, because these kind of questions are not asked in the examinations, like how it reacts with air. I haven't seen in the gndu one. They might be asked in other university. You can go through them, but they are not asked in this. So what are the action with this directly? They do not ask questions like this. Okay, so they ask things like BeCl2, why is it like this, and questions like that. That's why I will cover about that only. Okay, and if you'll message me separately for this one, you'll comment it down, only then I'll do for the chemical one. So we'll see you in the next video, where we'll be covering BeCl2 complete one, solvation and complexation tendency, and role of alkali and alkaline earth metal in the biological system. Stay tuned for that video, and hit the like button if you have seen this video this much far, and if I help you in the exams, then I need a like and a subscribe for the channel. Thanks for watching.